Alright, this is take two because I said something that I wasn't supposed to say in take one. Alright, so I'm going to have to do a bunch of videos. So QAnal is sort of my large project. I anticipate it taking a long time, probably a few years. And eventually I'm going to need to involve some other people. Sorry if you hear a fan. I live in Mumbai and it's June, and so if I don't have a fan on, then I melt. So if you hear the fan, I'm sorry about that. Um, So my main project, which is sort of my biggest project, is called QAnal. Stands for rational analysis. So Q is the standard mathematical notation. It's short for quotient. It means pairs of integers a and b, where b is not equal to 0. This is called a ratio, and so these types of numbers, which are written in this fractional form, these are called rational numbers because they're ratios, or alternatively quotients. And so QAnal is short for rational analysis. And so this started a few months ago, like December of 2020. It's June of 2021 right now. I was going to make a tutorial explaining how neural networks work. And the reason, there's 1,000 tutorials out there, but they all break down when they get to explaining backpropagation. So a neural network is just this algorithm for approximating functions. And backpropagation so it has, thousands and thousands of parameters, and it has this way of, you just kind of randomly initialize the parameters, and then you feed a bunch of test data into the function, and then look at the error, and then based on the error, there's a very deterministic way to update the parameters. And that works based on something called the chain rule. And what I discovered when I was trying to learn about these is that almost nobody who makes a tutorial about neural networks actually understands what the chain rule says or how the chain rule works. And I understand the chain rule, so I was going to make a tutorial where I properly explain the chain rule. And here I was explaining it. So what the chain rule says, it's very simple. It is the derivative of a composition of functions is the composition of the derivatives once you realize that the derivative is this matrix, and composing matrices just means multiplying matrices. So the derivative of f1 up to fk evaluated at x, because the derivative is something that's evaluated at a point. This is going to be just a matrix, and it's equal to the product of all of these matrices. So it's the derivative of f sub k, this is called a Jacobian matrix, is another word for it, evaluated at x. Then you multiply that on the left by the derivative of f sub k minus 1 evaluated at f sub k of x, because that's what the input of fk minus 1 is going to be, all the way, there should be 3 dots, all the way up to df1 evaluated at that horrible expression. But basically it's taking the Jacobian of each of these functions in the composition, evaluating the Jacobian at the point where the input of where the input to that function is going to be, and then multiplying all those matrices together. That's how you compute the derivative of a composition. If you took calculus, if you took single variable calculus, or even multivariable calculus, you'll get this retarded version that uses this partial derivatives, and that's just a stupid way to understand the chain rule. The chain rule is just composing a bunch of linear operators together, which means multiplying matrices. That's all it is. Anyway, before I made that video, I wrote some notes, and I've since learned that writing notes before a video is just it just doesn't work with the way I do things. Anyway, I sent them out to a couple people, and the responses I got back, I figured that it was going to be too elementary, and what I discovered was that the people in my target audience didn't actually know basic linear algebra, and these were, talented programmers who just didn't know. I got questions like, why don't you write the matrix multiplication in the opposite order? That would be a lot clearer. And apparently these, here's a fun fact about matrices, is generally if you have a matrix A and a matrix B, and you multiply A times B, in general, that is different from B times A. And these people didn't know that. That's like the first most basic fact about matrices. These people didn't know that. And so it's like, okay, I'm not going to do a whole linear algebra series, and the reason is because there's 50 linear algebra series on YouTube, and they're all going to be better than mine. And the basic problem is that is not that linear algebra is difficult. Linear algebra is a very simple and straightforward subject. The problem for these people is that they can't read mathematical notation. And, you know, you see something like this nonsense, and you can't really blame them. And, you know, it's funny, a lot of programmers actually really understand mathematics quite well, but they, if you write the same idea in code versus in mathematical notation, they'll instantly understand the code, but the mathematical notation doesn't make any sense, and kind of hard to blame them. Anyway, because mathematical notation is just, I mean, look at this. Look at this. And this isn't even correct either. Anyway, that's not the point. So what the hell does any of this have to do with QAnal? So, oh, that's right. So I was going to say, okay, well, you know, if you look at any linear algebra textbook, they always start with Gaussian elimination, and there's a reason for that. Gaussian elimination is just like if you have a system of linear equations. So if you have like 3x plus, I don't know, 7y plus 8z equals 4, and then, you know, 2x plus 3y minus 15z is equal to 9. I'm not very good at thinking of random numbers, apparently. 14x, I have no idea, minus 11y plus 2z is equal to 15, let's say. That looks like it's solvable. Anyway, you can, you know, what you're looking for is the set of numbers x, y, and z such that all three of these equations are true at once. Kind of the simplest way, the way you'd solve this is, well, first you rewrite this as a matrix problem, so 3, 7, 8, 2, 3, minus 1, 5, 1, 4, minus 1, 1, and 2. You take this matrix times x, y, z. This is equal to, I think it was 4, 9, 1, 5. And so you take this system of linear equations, you rewrite it as a matrix problem. Kind of the, if this matrix has an inverse, then you can just say, well, let's call this A times, let's call this big vector x, is equal to the vector b. And so maybe a simple, obvious way to solve this is, well, if you can find an inverse matrix to A, then you can say A inverse times A times x is equal to A inverse. Remember, you have to do multiplication on the left to both sides times b. Of course, these are just going to cancel, and then so now you have a solution to x. And then, so now there's a question of how do you find an inverse matrix, and what happens if the matrix isn't invertible? And there's a very straightforward algorithm called Gaussian elimination that kind of solves both questions all at once. And you know, a lot of linear algebra is really just sort of putting lipstick on Gaussian elimination. It's sort of the most basic thing in linear algebra. So if you want to understand linear algebra, if you kind of understand Gaussian elimination, it's pretty easy to kind of understand everything else. And so I wrote some code, I think it's still on GitLab somewhere, to do Gaussian elimination. You know, it's, I think I've deleted it, but it's somewhere in the history of the QAnal repository. Anyway, what was I going to say about that? Oh, that's right, I wrote code to do this, and it was very, very annoying because, you know, doing this involves a bunch of division. And one thing you'll discover, if you work with computers, if you program at all, is that computers are very, very bad at division. Computers can do amazing things, but they can't do division. Let me show you an example. Just blow that way up. Okay, that's Python 3. Let's try Python 3. Okay, 1 divided by 10. 2 divided by 10. 3 divided by 10. Let's just try something. double equals is a comparison test. Oh. And the reason is because 0.1 plus 0.2, the way computers handle division is with this just unbelievably stupid idea called floats, which means it always stores, I think, 54 binary digits of precision. And for some reason, God has decided that in computers, whenever you're doing division, you always need 54 binary digits of precision, or something like, I can't remember exactly how they work. Oh, and that's the thing about floats, is they actually work different on every single machine. Not every single machine. The standard is about how floating point arithmetic works is ambiguous. It's really just dumb. And so I'm like, okay, well, floats are stupid, and it would make this algorithm way more complicated than it needs to be to use floats. And so I said, well, instead I'm going to implement a data structure for rational numbers. So rational numbers, again, these are these quotients, a divided by b. And that's actually very straightforward to do, and that's what I'm going to talk about in the rest of this. Oops, that's me reading a book. What was I saying? Oh, and so... And I break my code all the time, so I have no idea. So let me just show you. This may not work. 110. Okay. So, by the way, right now I'm kind of experimenting with an idea, which is that every number is a quaternion. That's kind of what I'm thinking about right now. I'm not sure if I'll stick with that. It's the problem. The problem I'm having are what we call waterbed problems, which is that if you try to reduce the amount of complexity in one area of your code, it kind of pops up in other areas of your code. And I was talking to Craig Cannon about this. I did a podcast with him that's on my BitChute. You can't go on YouTube, kind of explaining more about the premise of QAnal. And it can't go on YouTube because, we talk about politically incorrect stuff and we're cursing and saying all sorts of things you can't say on YouTube. I will try to put a link to that. I might not remember. Go find me on BitChute. It's the same handle. Anyway, so there's a pretty printer though. Anyway, and so it prints it in Lisp notation, and eventually I got to write an interpreter, and then I can just put a telnet server up, and so anybody can just telnet into, QAnal.orangepill.healthcare and play with this. But that will take me a few days to do, and I haven't gotten around to doing it. But 210, that's Q15. It knows how to reduce fractions. 3/10. Okay, but the point is that QAnal plus QAnal Q. Let me plus equals fun. PP equals fun. QAnal PP1. Okay, and let's just test that. Okay, and this will just cut down on. Q equals fun, QAnal Q2, and then plus equals fun, QAnal plus, let's do plus 1. Now plus 1, that just means the arity of the function, and so this means I send it a list. So if I do plus 1 of 3 and 4, it'll say plus/1. So this notation means QAnal, that's the module, this is the name of the function, and this is how many arguments the function takes. And so there is a QAnal plus 2, and let's call this plus 2, and that takes 2 arguments. Plus 1 just is a list, and it just folds over the list and adds the successive arguments. But anyway, so let's do plus 2 of Q of 110, and Q of 210. That's that quaternion nonsense. This is a tuple in our lang, but let's pretty print it. And let's just see, is this is the equals operator Q of 3, 10. Hey, that's true. And 0.1 plus 0.2, that's false. So this is the basic premise of why QAnal is a good idea, is that it solves this problem. And this is just a really annoying problem with computers. I have no idea. I guess kind of in 1970, which is I guess when the float idea came around, was when computer hardware sucked. And maybe the GCD algorithm, which is the kind of core algorithm, which is what I'm going to get to, behind this, maybe that was too expensive, and so it made sense to use float. On a modern computer, I mean, the GCD algorithm is not a bottleneck, right? We have, the average application now runs in, it's written in JavaScript. It runs in a JavaScript interpreter, which is written in C++, which is running in a web browser. Why on earth we're still using floats it's baffling. And so I want to kind of write a large array of sort of common numerical things you need to do with computers that doesn't use floats. And there's in fact, a whole branch of mathematics basically called numerical analysis, where I don't want to paint with too broad of a brush, but I'm going to, anyway. There we go. Most of numerical analysis is just trying to get around floating point error, which is insane. Like, it's just, why? Anyway, so I originally just started writing QAnal so that I could write a Gaussian elimination program that didn't have this float nonsense. And then I kind of realized, well, first of all, this is clearly a good idea. That doing a lot of basic computer arithmetic type things, a lot of basic numerical calculations without floats, that's clearly a good idea because just using rationals. I tried to find other people who had, because, everybody knows about the problem with floats. I tried to find other people who had tried to solve this problem. I found this one dude, I can't remember his name. He's at the University of Singapore. He's a white guy, American accent, and he had some other data structure, I can't remember what it was called, where he was trying to fix the float problem. But he was making the same basic mistake that floats make, which is this idea called the real numbers. And these are the rationals and irrational numbers. So, for instance, the square root of 2, there is no fraction such that when you square it, it equals 2. That's a fairly simple proof. You can go look it up. Pi, there is no two integers such that when you divide them, you get pi. E, which is Euler's number, that's another example of an irrational number. So a number where there are no two integers such that when you divide one by the other, you get this number. And these are sort of a bit of mathematical fiction that was invented for good mathematical reasons, but unfortunately they don't fit into computers, and when you're actually doing a calculation, you can't use these really. You can only use them when they cancel. So you can only use square root of 2. You can either do an approximation, or you can rely on the fact that you put it into an equation such that it gets squared, and at the end of the day you get a rational number out of it. Really, all actual numerical techniques use rational numbers. And in fact, they don't use rational numbers, they use floats, which is just stupid. You don't need floats anymore. Why we use them is beyond me. Floats are even a big enough problem that, I can't remember her name, I think Vanessa McHale, and don't quote me on this, I might have the details wrong, but floating point error is enough that in different statistics packages it can be enough to change whether or not some statistical effect is statistically significant. Like, floating point error is that big. It can change correlations by, a big enough percentage that it could actually change the conclusion in a paper. That's ridiculous. We don't need any of this. And so that's the basic idea of why I started doing QAnal. So let's get into how this works. So halts. Actually, I don't want to halt. Let me see. Let me tmux. CD src. And this is very unstable. I have code examples from previous videos that don't work anymore. I'm constantly updating this, but and I'm always experimenting with ideas. I haven't really. Before I get into this, I should tell you kind of the basic premise of the subject, which is, well, sometimes there are times where you do need to take a square root, or you do need to deal with pi, right? And instead of pretending that the square root of 2 is something that you can treat as if it's an exact quantity, instead what I'm going to do is carry along information about the error, propagate error properly. There's a whole study, I guess, in science about how to propagate errors. I looked into some of that. There doesn't appear to be any logic behind any of it. It all just seems ad hoc. At least I couldn't figure out what the logic was. It's either making some extremely... So there was one thing which is you sort of take a matrix of, what is it, the variance-covariance matrix between all of your variables, and that's assuming a lot of geometry about the way your variables work. Then there's this really weird idea called significant figures, which, as far as I can tell, there's absolutely no logic behind it. It's all just made up. Or it's based kind of off it sort of does seem kind of like it's based on the encoding theory idea, where you sort of keep the encoding length constant if you treat a decimal number as sort of a code, but it doesn't seem to map super well onto that. And then even then, when you actually are doing these calculations, none of this factors in floating point error, which seems complete. Mathematicians and physicists seem completely oblivious to that. But anyway, so I still don't know how to deal with this precision problem, and that's kind of the biggest idea with QAnal. So QAnal is really split. So here we have QAnal, and it's split into two subjects. So exact, things that are exact, so these are fractions, and things that are precise, and these are different words. And so exact, this is pretty straightforward, and this is what I'm going to talk about at first. Precise, these are things that are approximate, so things that have the notion of precision. Or not idea, notion. Approximation. And so this subfield is abbreviated XAnal, and this is abbreviated preanal. And this is pretty easy, straightforward, meaning kind of mathematic. This is very mature. This is already well developed. Everybody else has already done the work for me. This is the novel part. And I actually, this is easy. I already know how to do most of this, meaning other people have already figured out. This is completely novel. This seems like unexplored territory, and I actually don't know how to do this. My current idea is that, well, when you're actually doing a calculation on computers, there's all these transcendental functions that theoretically exist in math, like sines and cosines and tangent and arctangent and logarithm, and those are all fine and dandy. They don't actually exist on computers. When you ask for sine, your computer just computes a really long polynomial. When you ask for the sine of 3, it just plugs it into a polynomial, or maybe uses a table or something like that. And my idea is, well, instead of say sine of x, and this is just some polynomial of x. I'm going to use p for polynomial. Instead, what I'm going to do, this is my current idea, I don't know if this is going to work, sine of x plus some variable called epsilon sub x, which is the error term of x. And then you just plug this into the polynomial. So for instance, if p of x is equal to x, so let's say p of x is equal to x squared, then p of x plus epsilon x, epsilon sub x, this goes to what that would be, x squared plus 2x epsilon sub x plus epsilon sub x squared. And so all you do is keep track. I have no idea if this is going to work. This is kind of my current idea, which is generally you just keep track of how the error gets transformed. And then what you do is say, if you have a bunch of variables with a bunch of error terms, then you can, after the fact, impose whatever probability distribution you want on the error terms. And that's actually, I think, the proper way to handle uncertainty, is to recognize that with computers really have two tools. Matrices, well, that was bad. Matrices and polynomials. Actually, my current handicap right now is kind of trying to figure out how to do representations of polynomials. Polynomials are representing them, matrices representing those computationally is quite straightforward. Writing a matrix library is pretty easy. A polynomial library, there's all sorts of issues with unique representation, and that's actually, so unique representation, that's actually good initial subject to talk about. But anyway, so unique representation is really, really important with in engineering, in computing. So what do I mean by that? So if you take the fraction 1/2, well, this is equal to a lot of other fractions. So for instance, this is equal to -1 divided by -2, which is equal to 2 divided by 4. And so there's all these different fractions that are equal to each other. And you have the same thing with polynomials. So for just here, you had, for instance, x plus epsilon sub x. This is equal to x squared plus 2x epsilon sub x plus epsilon sub x squared, and square. And polynomials, the unique representation issue with fractions is actually pretty easy to solve, and that's what I'm going to talk about right now. The unique representation issue with polynomials is really not as easy. It's not as easy, or at least it doesn't seem as easy right now. Once I figure it out, I'll claim that it was easy the whole time, but I haven't quite figured out how to do that. The problem with polynomials, you can adding them, multiplying them, that's all very straightforward. As soon as you need to divide them, then things get hairy. And then additionally, with polynomials, I made this kind of, for kind of an experimental reason, I chose to have every number be a quaternion. Now, the problem with quaternions, and there was a good reason to do that, which is sort of that if you want to do 3D geometry, though that's very intimately connected with quaternions, and if you watch my homology video, you may have gotten a hint that I think that I can make the subject of electromagnetism much simpler, and I'm pretty confident that I can. And one way to do that is, instead of using this nonsense about dot products and cross products, you use quaternions instead, which, whatever, are a little bit more involved, but I think ultimately you get a cleaner theory out of it. I think I will probably also fix the sign convention with charge, or current, I can't remember which one it is. I think they're the same. Yeah, it's charge. Maybe call it anti-charge instead. If I'm going to redo the theory, I might as well do it right. What was I going to say about that? I don't know. I lost my train of thought. Anyway, let's talk about unique representation of fractions. So that's actually the lesson one. So the first problem you have if you want to do a data structure with fractions is how do you deal with this problem of there's a lot of different fractions that look different but are actually the same fraction? And the answer is called reducing a fraction. And so I'll call a fraction reduced. And so reduced if the bottom is strictly positive, so it can't be 0 because you can never divide by 0. And so if the bottom is strictly positive, and the top can be positive, negative, or 0, and top and bottom have no common divisors. So you notice that in here, 2 and 4 have a common divisor, which is 2, which is why if you divide the top and the bottom of the fraction both by 2, then you get 1 divided by 2, which is the same thing as over here. And so now the question is, how do you get rid of common divisors? So the naive way is to factor both numbers. But factoring numbers, especially large numbers, is a very, very difficult problem. It's so difficult, in fact, that all of modern cryptography basically relies on the fact that it's too hard to factor numbers. So, like, literally, if somebody figured out how to factor numbers very quickly, all of everything would break in the world, because everything in the world operates on the premise that factoring numbers is too hard. It really is that hard. It really takes that long. But one thing you can do is there's this observation. So the first fact, and I don't know of a good proof of this. I've tried to find a proof, and I haven't found one that I like. And I don't like proofs for the sake of proofs. I like proofs if they explain why something is true, if after reading the proof you understand why something is true. A fact is that every integer can be factored uniquely into prime numbers. Uniquely prime numbers up to, what mathematicians will use this phrase, up to a reordering of the factors. What that means is that if you pick a canonical way to order the factors, so you say order the factors from least to greatest, then the factorization is unique. So meaning, let's say 6 is equal to 2 times 3. These are both prime numbers, and there is no different set of prime numbers, or I shouldn't say set, multi-set of prime numbers, such that when you take their product you get 6. There just isn't. And this is equal to 3 times 2, but you pick an ordering, let's say least to greatest, and then it's unique. This is supposedly a theorem. I haven't seen a proof that I found very convincing, or clear at least, but I will just take it as an empirical fact. Now, here's another fact. Any common divisor of two integers divides their greatest common divisor. Now, let me explain this. And it's actually very easy to find the GCD. The GCD is a very easy thing to find, and I'll explain how to do that. But this is the saving grace. If this wasn't true, oh, and let me just show you why this is true. Let's just pretend that you have two numbers, let's call them x and y, and I'm going to pretend that x can be factored into a, b, c. And then y is equal to b, c, d, where these are these are the prime factorizations, and they're listed in order from least to greatest, let's say. Okay, well, the common divisors of these are b, c, and let's say b, c, and then there's trivial divisors like 1, but let's not be stupid. And their greatest common divisor is clearly bc, right? That's their greatest common divisor. Okay, and all of their divisors divide the greatest common divisor, because the greatest common divisor is just you can just think of this as a list of prime numbers sorted by least to greatest, though the greatest common divisor is just the intersection of the two lists. And so any common divisor will be a sublist of that intersection of the two lists. So that's why any common divisor of two integers divides their greatest common divisor. You can also just see by this same basic argument that x times y is equal to the GCD, yes, this is correct, of x and y times the least common multiple. And where the least common multiple is a times b times c times d, it's the exact same argument. So the GCD will be b times c, and the LCM will be a times b times c times d. Well, when you multiply the two, you double count their GCD. So that's why this is true. So the x times y, this would be a, b squared, c squared, d, and this is equal to bc times a, b, c, d, right? You're just double counting the GCD, which is why you have to multiply it. So this is actually another good way to find the least common multiple. It's very easy to find the GCD. We're going to go over that. Now, here's a lovely feature of mathematics, is most of mathematics is word games when you break it down. You'll hear this nonsense like, oh, a fractal is a set with fractional dimension. What the hell does that mean? So GCD does not mean the greatest with respect. GCD, if you're a normal person, you think this means greatest with respect to the normal order on the integers. So for instance, 3 is greater than 2. Okay? That's not what it means. It means greatest with respect to the divisibility graph on the integers. And that's actually important to understand. With to the divisibility graph. Now, what the hell is a divisibility graph? Let me just give you a short little example. So at the top of the divisibility graph is 0, and at the bottom is 1. And then let's say I'm just going to draw a subset of it, 6, and then 3, and 2, and 1. And so this has an ordering to it, so maybe let's just draw arrows. Maybe the arrows should go in the other direction. Oh, that's annoying. Let's just draw the arrows in the obvious way. And so the order, so if you have a sort of directed graph like this that doesn't have loops, sort of that only goes in one direction, this is, I might have the wrong terminology here. I think this is called a Hasse diagram. You can go look that up, see if I have the right terminology. But anyway, this determines, the fancy term is partially ordered set. So according to this relationship, 2 is less than or equal to 6, but 2 and 3 are not comparable. Not comparable, because neither one is less than or equal to the other. And so what the GCD is, so let's take the GCD of 20 and 15. Well, this is obviously equal to 5, right? And so maybe one way to see this is 5 times 2. Let me write this in proper order. 2 squared times 5, and this is 3 times 5. So the GCD is 5. But the proper way to think about this is, oh boy, I'm gonna try to draw this live. Maybe I'll draw it upside down. So we have 1, we have 2, we have 4, and then let's go with 20, and then 20 also, and then 5 is a direct descendant of 1. So the prime numbers are characterized by they are directly above. I'm drawing this upside down. They are directly above or below, depending on your orientation. They're directly above 1, and then 3 times 5 gives us 15. Okay, and what the GCD is the, let me draw this the right way, because this is just getting confusing. Forget this. So 20, but at least I know how to draw it now. 15, then we have 5, and then 4. I better be recording. Sometimes I do like a whole thing and realize I haven't been recording. I am recording, that's good. We have 4, oh boy. That's a terrible arrow. And then 2, and then 3, let's put 3 between 2 and 4. And then 1 is at the bottom, and of course 0 is at the top of the divisibility graph, which is 0 über alles. Okay. And so what the GCD is it's the smallest number, which is an antecedent. It's the smallest number with respect to this divisibility graph that is an antecedent of both 20 and 15. And then their LCM would be, if you kept this, ignore the 0 for a minute. The LCM, if you kind of completed out this graph and drew out the whole graph, the LCM would be the sort of shortest node up here, which is a descendant of both 20 and 15, which would be the sort of smallest node on the divisibility graph. The fact that that is unique is a highly non-trivial result, and again, the fact that I can define the greatest common divisor is a consequence of the fact that factoring integers, there's only one way to do it, into prime numbers, and that it's unique. And if it wasn't true that factoring integers was unique, then we'd be in a lot of trouble here. So how do you actually compute the GCD? So it's important to understand that there's word games going on here, that it actually means greatest with respect. So a common divisor is you get the idea. It's greatest with respect to this weird relationship on these graphs. Graphs as in networks. And so let's just go into the QAnal code and actually see how this works. So xv qxz.earl. Let's just, I don't care. Okay, so So Z stands for Zolin, which is the standard mathematical notation for integers in the same way that Q. So this is the module for doing basic operations with integers. It exports three types, Z, ZNN, and ZP. Z is integer, ZNN is non-negative integer, ZP is positive integer. And it exports three functions, GCD1, which is just GCD of a list. So that operation, you can take the GCD of like 5 numbers. It's the same basic premise. It's the smallest node in that graph, or it's the biggest node in that graph, which is smaller than every one of the list. So it's an associative operation, associative binary operation in the language of algebra. And then modulo, and the reason I had to write modulo is, let me just show you. Is this Erlang? No, this is Erlang. QXZ, so every programming language has a function to compute remainders. So let's do 7 rem3. That's equal to 1. Okay, but if I do minus 7 rem3, that's equal to minus 1. Is that correct? Oh, and what I want is a number between 0 and 2. So QXZ modulo. Oh, modulo. I was wondering what it was getting hung up on. 7,3 gives the same result, and if I do minus 7,3, yeah, that's right. Because minus one is equal to 2 mod 3, right? Because mod 3, it's just modular arithmetic is like clock arithmetic. So if you imagine a clock only had 3 hours, in the same way that minus 1 is equal to 11 in normal clock arithmetic, minus 1 is equal to 11 mod 12, well, minus 1 is equal to 3 mod 2. Or, correction, minus 1 is equal to 2 mod 3. I got that confused. So, maybe let me... So, there. It's the same basic idea. So anyway, let's just look at the modulo operation just to show you what that is. I might have to. So it works like the remainder operator, except this always returns a result within 0 dot dot b. That's actually, oops. It should return between 0 and b minus 1. It will never return b. That was a mistake. So here, let me show you. If I do 12 mod 12, that returns 0. So it'll never return 12. That was a mistake in the comment. I gotta fix that. For simplicity, obviously correct behavior, b must be strictly positive. Okay. Modulo ab, when is integer a and is integer b, and 0 is less than b. I always write, whenever I put inequalities in programs, I always use less than or equal to, and that way you can visualize it as a number line and 0 is to the left of b. I always get confused when I have to like flip things around in my head, so I just have a convention. I always write it as 0 is less than b and never b is greater than 0. A rem b is just the normal remainder operator. There's one of two cases, so minus b is less than a remainder b, and so it's negative. So if you give it a negative argument, so we saw this when we did like minus 1 rem 12, that gave us minus 1. So the first case is when you have something like that, in which case you just add 12 and you get the correct answer. And otherwise it'll return a correct result between 0 and b inclusive on the left. That'll happen when you give it a positive number, and then in which case you can just return a rem b. Okay, so negative remainder. So I wrote these explicitly. You can make this more efficient, but who cares? There's two conditions. Neg remainder is minus 1 times b, so minus b is less than a rem b, and also a rem b is greater than 0. I just rewrote this down here, or down here. Okay, and then I rewrote this right here. Same thing. So, if we have a negative remainder, return a rem b plus b. If we have a positive remainder, return a rem b. That's it. Okay. What is this? This is GCD. Okay. Yeah, we'll get to this in a minute. Okay, let's look at GCD. So GCD of a list, it just does GCD accumulator. We'll get to that in a little minute. How to compute the greatest common divisor. So, by the way, the core idea of reducing a fraction, make sure the positive, here, let's actually look at this. Core idea of reducing a fraction, it uses this Q function. Okay, so quotient of anything with 0, that's an error, you're not allowed to divide by 0. Quotient of anything with 1, just put the integer up there. If the bottom is negative, multiply the top and bottom by -1. That way you get the bottom to be strictly positive. Q of top and bottom when the bottom is positive, the top is an integer, and the bottom is an integer. Okay. Then the GCD is QXC colon GCD of top and bottom. This is how you reduce a fraction. You divide by the greatest common divisor, and that'll knock out all of the common factors. And there you go. That's how it works. And so when we do QXQ Q of 2, 4, it computes the GCD, divides 2 and 4 both by the GCD, and div means integer division in our line. And it just works the way you expect it to. And that's nice. Okay. Let's look at the integer. I just answered this. I don't care. I don't care. Anyway, so greatest common divisor of two integers. Make sure both arguments are non-negative and the one on the left is bigger. Okay. And what this does is there's a couple of assumptions you want to make when you're doing the GCD. And the first one you want to make is that the left argument is bigger than the right argument and that they're both positive. Okay, so what this does is says when absolute value of x is less than the absolute value of y. So then it flips the two arguments. Otherwise, it just takes the absolute value of both arguments. So ABS is the absolute value. So GCD of x, y, when the absolute value of x is less than the absolute value of y, send them both to GCD plus, but flip the arguments. If the absolute value of x is greater than or equal to the absolute value of y, send them both to GCD plus as is. So here is abs y, abs x. Notice I flipped them. Here it doesn't flip them. Let's look at this GCD plus. Okay. GCD plus takes two non-negative integers and returns a non-negative integer. So GCD where the arguments can be assumed to be non-negative and in the correct order. That's the idea here. So GCD plus of x and 0 is always equal to x. Now, that is because x is at the top of this divisibility graph. And so if you take x and 0, well, what's the smallest, or what's the biggest, with respect to this divisibility graph, what is the biggest node that is less, say you're doing GCD of 20 and 0, what's the biggest node in this divisibility graph that is less than both 20 and 0? Well, obviously it's 20, right? And so that's all this is saying. So GCD plus of x and 0, that's x. Then there's a second case, and again, this x will always be greater than or equal to y because you're only calling it from the GCD function, and the GCD function already guarantees that. This is just for readability purposes. So GCD plus xy when x is greater than or equal to y. Now, this comment explains how this works. So, it's either 0 or it's not, either the second argument is 0 or it's not 0, and those are the only two cases of the function. Now, the idea here is to write x as q times y plus r. So for instance, 7 is 2 times 3 plus 1. So q is the quotient or the integer division of x and y, and r is the remainder, which is the outcome of that modulo function. Now, r was always going to be between 0 and y, inclusive on the left, not inclusive on the y. Now, if there's a number that divides both x and y, then you notice, let me blow this way up so that you can really see this. So x is equal to q times y plus r. Therefore, r, if you just reorient the equation, is x minus q times y. If you have some number that divides both x and y, then x minus qy divided by that number is still going to be an integer, because x divided by that integer plus minus q times y divided by that integer, well, everything there is still an integer, and you're dandy. Well, on the other side you have r. So any common divisor of x and y, so anything that divides both x and y, also divides the remainder of x. Therefore, just by this equation, any common divisor of x and y also divides r. So therefore, the GCD of x and y is equal to the GCD of y and r. And what we've done, this is why we assumed that x is bigger than or equal to y, and so this way we can just keep dividing it into a problem with smaller and smaller integers. And eventually you're going to get to a point where modulo xy is equal to 0, and so that's when you would call it with like GCD of 20 and 20. Okay. But you're just going to keep beating down, keep reducing it to smaller and smaller cases until eventually you get to the case where r is equal to 0. And that point, that's the GCD. And it's kind of this weird, recursion is a little bit magic, but it just works. And it works because it's based on solid logic. This logic is, you can't poke a hole in this logic. This logic makes perfect sense, but it's a bit magical. It's like, well, you know, there's like 10 lines of comments here, but there's 4 lines of code. It's a bit mysterious, like why does this work? But it just does. And it's surprisingly fast too. The GCD, I think, is a logarithmic order function of the order of the smaller of the 2 arguments. So it's actually a very, very fast algorithm. Why floats are standardized and fractions are not is beyond me. Anyway, so yeah, so that's the basic unique representation issue with fractions. Is you divide the top and bottom of the fraction by the GCD. You make sure that if there's a negative sign, it's in the top of the fraction. You could either pick the top or the bottom for the negative sign. I just picked the top. And there, you solve the unique representation issue. To add 2 fractions, okay, well, you make a common denominator. So q of TL times BR plus TR times BL, it's the exact same thing, divided by BR times BL. So this is sending it to that Q function that we just saw. Oh, I should have shown you the, if it asks me that, shut up. I don't care. Open read all. I don't care. Anyway, this GCD accumulator function, it's just relying on the fact that GCD, oh, that's a thing, is that once you get to 1, because 1 is at the bottom of this graph, then you can just quit. Right? Once you get to 1, you're never going to find a number lower than 1, so you can just quit. And if 2 numbers have the property that their greatest common divisor is 1, that means they have no common divisors, in effect. And in that case, the numbers are said to be relatively prime or coprime. Let me write those 2 down. relative prime and coprime. These two mean GCD. X and Y are relatively prime or coprime if the GCD of X and Y is equal to 1. That's what that means if you hear that term. There we go. So GCD accum, if you calculate it and you get to 1, so this is shortcutting if you ever get to 1. So when it's actually called, it starts with 0, because 0 is the most neutral argument. It's at the top of the divisibility graph, and then you slowly crawl down the divisibility graph. I'm going to make an animation at some point that shows how this works with respect to the divisibility graph. I haven't done that yet. But if you get to 1, you can just stop there, because it's the same reason that if you're like taking the product of a bunch of things and you end up with an accumulated product of 0, right, you multiply by 0, you don't need to multiply the rest of the list. The product is 0. You can just stop once you hit 0. In the same way that when you're taking the GCD, once you hit 1, you can stop. The answer is 1. Once you've hit the end of the list, you return the accumulator. If you have a new item in the list, you GCD it against the accumulator, and then just keep going. It's very simple. Okay, let's look at the quotients again. Why are you... Okay, quit. There's just a bunch of convenience functions. 1 over just divides the fraction. 1 is the Q11 minus, you know, you have subtraction, you have all the normal arithmetic. Convert from an integer, divide, you know, they're defined in the obvious way. The kind of only really interesting one is times, here we go. Oh yeah, so we can look at times accum. But times, to multiply A divided by B by C divided by D, it's AC over BD. It's exactly the same thing here. Let's look at times accum, because you can see the same basic idea. So times accum, if you get 0, if you're multiplying a bunch of numbers and somewhere along the way you multiply by 0 or you get 0 as the accumulated product, you can stop because the rest of the product is going to be 0. Same logic as the GCD with 1. Multiplication, it's the same basic idea, right? You get to the end of the list, you return the accumulator. If you're not at the end of the list, multiply the accumulator by x and continue going along. It's very simple. And that's the basic idea. That's the most core basic problem solved, which is unique representation of fractions. You can do linear algebra pretty straightforwardly from here. I was having code complexity problems because I had too many types, and so I was trying to, you know, my background is not Erlang, it's Haskell, and I was trying to basically shoehorn the idea of type classes into Erlang. If you're familiar with Haskell, you know what type classes are, and it didn't work, and it just introduced so much peripheral complexity into the code. And I talked to Craig Cannon about this, and he's a very experienced coder, and he told me basically that I should just have one straightforward graph of numerical types, and I typecast everything to the top type. And so I said, okay, well, I'll just make everything quaternions, which is why you have, you know, this, instead of QXQ, QAnal. QAnal is just a module that does all the typecasting and everything. So QAnal Q, it'll return a quaternion instead of a rational. Typecasts everything up to the top type. The problem here is that quaternion multiplication is not commutative, and that seems to be introducing waterbed problems elsewhere in my code. And I'm kind of getting the sense that polynomials are actually not maybe the right. I think they're the core idea of taking x and adding epsilon to it, and that's actually the correct idea, I think. But polynomials, they don't seem to agree very well with the way computers think. And that to me is telling me, maybe there's something more going on here. I'm not sure. I got to think about this more, do a lot more research. Um, and so I haven't been working on this, or I mean, I have been working on this. I work on it every single day, but I haven't been updating the code a lot because I've been kind of doing more mathematical research. I don't know enough about polynomials either, and so I've been trying to learn about that. There's a lot going on. Um, uh, anyway, that was all I wanted to talk about. I wanted to explain how the GCD algorithm works, explain the basic premise of QAnal, show off a little bit of, hey, look, I can do division right, and floats can't. I can also do, if you look at the homology video I did, I got to do more on algebraic topology. I wrote an 80 pages of notes for that video, and I tried to do like all 80 pages in one take, and I ended up doing like 50 takes, and it just was a disaster. It took me like months, and I eventually was like, okay, I'll just pick like 2 pages out of the notes and do that. And that video ended up being 30 minutes long, and that was 1/40th of what I wanted to talk about, and I was so burned out at that point. I haven't gone back and revisited the topic. I got to go back and do that. But anyway, in that video, I was using an earlier version of QAnal, and what I was showing was that there's this problem with it, which is you have, you know, here we go. You have some circuit. I think you had a circuit, and you have the basic laws of circuits are not Maxwell's equations, Kirchhoff's equations, and one of them is the loop rule, which I can't remember. It says something like, what is it? The sum of voltage changes over any loop is equal to 0. And there's an important caveat to that, which is that you can only derive as many equations from that as you have independent loops. And so then there's a question of, well, how do you systematically count independent loops? Okay, well then there's this whole other class of problems, which is, well, if you look in a physics textbook, they'll give you a wrong answer, which is the Euler characteristic. So here, which is vertices minus edges plus faces is equal to 2, which is derived from the Euler characteristic, and I'll look up. Just look up Euler characteristic stereographic projection if you want to just see a quick visual demonstration. The basic premise is, I'm not going to explain that. This is only true, however, for planar graphs, and if you've done enough planar graphs means that you can draw the circuit in such a way that edges only intersect at a vertex. And there's a lot of circuits for which that isn't true, and in those cases maybe the Euler characteristic might not actually be 2. I'm not 100% sure. Anyway, what was I going to say about that? Oh, there's this problem of counting holes, and it reduces to a linear algebra problem of finding the null space of a matrix. And it's solving the circuit boils down to I think it was just a matrix problem. And anyway, and QAnal could solve it exactly, and Python can't solve that exactly. Maybe something like Sage or Mathematica could solve that exactly, but QAnal can also do it. Anyway, if you want to see kind of an earlier version of QAnal that had I deleted all the matrix code because I've rewritten QAnal like 6 times. I am going to put back in the matrix code. I gotta kind of decide if I want to stick with this quaternion thing. I actually kind of like it, but it is, I don't know. Anyway, that's all I want to talk about. thank you for watching if you watched all the way to the end. I'm going to do more videos on like this, going over just more things, just kind of talking about things. Anyway, if you want to learn more about this, go look at the podcast I did with Craig Cannon on BitChute. Oh, and another thing, if you like doing video editing, I've got like 20 hours of podcasts just sitting on my hard drive that I don't have time to edit, and I need to edit them because, Craig always brings up some personal information, or sometimes I do that. I or there's information that we need to black out or something like that, and I just don't have time to edit them. I also am not very good at video editing. I literally use FFmpeg on the command line because I can't stand GUIs. So, if you're good at video editing and you like that type of thing, please send me an email. My email's plastered all over GitLab, so just go look at my GitLab. It's gitlab.com/Dr. AJ Kumar. I actually don't remember what my email is. It's Dr. AJ Kumar at ProtonMail. That's what it is. Anyway, yeah, please, yeah. That was what I was gonna say. If you like video editing, I need somebody who's good at video editing and likes video editing, and would like to go through 20 hours of podcasts and edit out all the personal information, and black out people's names and shit like that. Anyway, thank you for watching. Bye bye.